Welcome back to the deep dive. This is where we take your sources and, well, help you pull out the key insights.
We cut through the noise for you.
Exactly. And today we're diving into something super practical, but, often kind of tricky in front-end development.
Network requests.
You got it. Specifically, we're unpacking strategies for request caching and cancellation. This is all based on the material you shared with us.
That's good stuff. Really fundamental for performance and reliability.
Think of this deep dive as your shortcut, really, a way to get your head around building web apps that feel faster, more resilient, even when the network's being difficult or users are clicking everywhere.
Absolutely. The material gives a great overview of these patterns.
Mm.
It's all about smoothing out that user experience, making the app feel solid by being smart about how the front end talks to the back end.
Okay, let's unpack this then. So the first big piece the sources really dig into is caching.
Right. The core idea is just saving results from requests so you don't keep hammering the server for the same data. Makes things faster.
So what are the main ways the material mentions we can actually do this on the front end?
Well, the sources lay out a few common ways, and they each have their pros and cons.
Okay.
The simplest, often the quickest for immediate use, is the in-memory cache.
So that's living right there in your JavaScript, maybe in like Redux or Zustand or even just React context.
Exactly that. The data is stored right in the application's running memory.
Super fast access, I bet.
Yeah, the huge pro is speed. It's almost instant. But the equally huge con, as the material points out, is it just vanishes. Gone the moment the page reloads or the user closes the tab.
Right. Totally temporary. Great while you're there, but no help if you refresh or come back later.
Precisely. It's ephemeral.
So for something a bit more persistent, the sources bring up browser storage, like
No.
local storage and session storage.
Correct.
Yeah.
These use the browser's own storage mechanisms. The key benefit here is persistence. Local storage that keeps the data even if you close the browser and reopen it. Session storage, though, that only lasts for the session. Usually that means the specific browser tab.
Oh, that per tab detail is important. Good call out in the source.
It is.
Yeah.
The difference from in-memory, well, your JavaScript still has to actively talk to the browser's storage API to get the data back out. There's a tiny bit more overhead compared to just grabbing it from memory, just a fraction. But it's there.
Okay, makes sense. And then there's a totally different way, the HTTP cache. This isn't really about our JavaScript code storing data, is it?
No, not directly. This is about using standard web protocols. It's mainly controlled by HTTP headers.
Yeah.
Things like cache control, which the server sets in its response.
So you're basically telling the browser, hey, you can hang on to this response for, say, an hour.
Exactly. You tell the browser how long it can consider this response fresh and just reuse its own stored copy. The browser then handles the caching logic itself for later requests to the same URL.
The big win there seems to be offloading the work. Less JavaScript logic for us to write and manage.
Definitely. It pushes a lot of that complexity away from your front-end code and onto the browser and the server infrastructure. The source does note, though, it's primarily effective for GET requests. That's a limitation compared to the client-side storage where you have full control.
Okay, so we've got these different tools in the box. In-memory, browser storage, HTTP cache. When does the material say we should strategically use caching?
The sources are pretty clear on this. Caching is ideal for idempotent KETs.
Idempotent, meaning requests that don't change anything on the server if you repeat them?
Precisely. Retrieving data where asking again gives you the same result and has no side effects. Think fetching a list of users, getting product details, reading an article. You're not changing data, just asking for it.
So caching avoids pointless server load and makes the UI feel snappier for the user.
Dramatically snappier, especially for data that doesn't change often.
And that also covers the idea of requests repeated in a short time, yeah. Like if a user clicks an item, goes back, clicks the same item again.
Exactly. It stops you doing the same work over and over for data that's likely still perfectly valid within that user session. The basic flow, no matter which cache type you use, is generally check the cache first.
Right.
If it's there and it's fresh, use it. If not, then go fetch from the network. And if that fetch succeeds, you update your cache.
Simple enough. Check, use, or fetch, update. Okay, that handles getting data efficiently. But what about the other side of the coin? What happens when a request is already flying, maybe a slow database query, or worse, something that changes data and the user just, bang, navigates away or closes the tab?
Yeah, now we're getting into a really critical and honestly often overlooked area. canceling requests on reload or navigation.
Why is it so critical?
Well, if you have asynchronous work going on, especially write operations, think post, put t, delete requests from submitting a form, and the user leaves the page while that's in flight, letting it just continue in the background can cause some real headaches.
Headaches beyond just, like, wasted server cycles or bandwidth.
Oh yeah, much bigger problems. You could end up with inconsistent database states.
How so?
Well, imagine a multi-step form, maybe creating a complex order. Step 1, save some initial data. The user hits next, that request goes off. But before Step 2's request even finishes, the user navigates away. The server might be left with a partial, half-baked order record that's unusable or just wrong.
Oof. Yeah, I can see that.
And you also risk race conditions. Say a user quickly submits a change, navigates away, maybe gets distracted, comes back to a different page, and triggers another related action. That original request might finally complete after the second action, potentially overwriting or messing up the state established by that later action. It becomes unpredictable. Chaos, basically.
Wow, okay, yeah, that sounds pretty bad. Not just messy, but potentially corrupting data. So how do we stop this? How do we reliably cancel these from the front end? The sources point strongly to AbortController.
AbortController, that's the modern standard web API way to handle this. Think of it like this. It gives you a special signal object. You create a controller, new AbortController. You grab its signal property, then you pass that signal into your fetch call. Libraries like Axios support it too, and modern XHR.
So the request now knows about this signal.
Exactly.
Yeah.
And then when you decide, okay, time to cancel, maybe because the user clicked away or the component unmounted, you just call controller.abort.
And that just stops the request.
It signals the browser or library to abandon the request. The promise associated with that fetch call will then reject.
Ah. And the material mentioned catching a specific error, abort error. Why is that bit important?
Yes, very important. When you call abort, the fetch promise doesn't just reject with a generic network error. It rejects with a specific error object whose name property is abort error.
Okay.
This is crucial because it lets your error handling code tell the difference between oops, the server is down, or network connection lost versus nope, we deliberately canceled this because the user left. You don't want to show a scary network error pop up if the cancellation was intentional, right?
Right, you just, well, ignore it perhaps, or handle it silently. That makes total sense. It's a clean way to manage that specific scenario.
Exactly.
So we have the tool to signal cancellation, the AbortController. But how do we know when to pull the trigger? When do we call abort?
Right, that's the other piece. You need to monitor navigation or load events. You listen for signals from the browser or your framework that tell you the user is trying to leave the current context.
Like what kind of signals?
Well, the classic browser one is the beforeunload event on the window object. It fires just before the page is about to be unloaded.
Okay.
But if you're in a single-page app using something like React Router, Vue Router, Angular Router, you probably wouldn't use before unload as much. You'd hook into the router's events instead, like when the route is about to change.
Ah, so framework-specific hooks.
Often, yes.
Yeah.
The core idea is the same. Detect the leaving event, then trigger your cancellation signal.
So the front end can basically hit its own stop button on pending requests when the user decides to bail. That feels much tidier, much safer for the client-side state and performance.
It definitely helps the front end clean up its own mess. But, and this is a really critical point the sources bring up, especially for those write operations we talked about.
There's a catch.
Well, it's not a catch, but a necessary counterpart, ensuring backend idempotency and safety.
Right. Just because the front end asked to cancel doesn't mean the server didn't already receive the request or even start processing it before the cancellation signal propagated.
Exactly that. The request might have hit the server, maybe it started processing. Maybe the network cut out just after the headers were sent, but before the full request body arrived. If the backend isn't prepared, you can still end up with partial data, or, if the user retries, duplicate entries.
So front-end cancellation isn't a silver bullet for data consistency.
Not on its own for writes, no. That's where the source highlights using idempotency keys.
Okay, explain this again. It's like a unique ID for each specific attempt at an action.
Yes, precisely. Your front end generates a unique identifier, like a UUID, for a specific logical operation. Say, submit this specific order. You send that ID along with the request, maybe in a header, or the request body.
And the server.
The server, when it receives a request with an idempotency key, first checks if it's already seen that specific key before and successfully processed it. If it has, it knows this is a duplicate attempt, maybe a network retry, or the user clicking submit twice.
So it can just ignore the duplicate.
It can safely ignore the duplicate write operation. It might return the result from the original successful request, or just acknowledge it without doing the work again. This prevents creating two orders when the user only intended one.
That's clever.
It's essential for robust APIs. The source also briefly mentions that for really complex multi-step things on the back end, the server might need built-in rollback logic or compensating actions to clean up any partial state if an operation gets interrupted midway or is detected as a duplicate later on.
Okay, so that's the real safety net for writes. Front-end cancellation is like the polite way to leave the party early, client side, but back-end idempotency is what ensures the host doesn't end up with duplicate gifts or half-eaten snacks.
That's a good analogy. Yeah, it's a layered defense. You need both for truly robust handling of writes in unpredictable network conditions.
So bringing this all together then, based on the material, how do these pieces, the caching, the cancellation, the idempotency, fit into a solid overall front-end strategy?
The combined approach the sources describe is pretty powerful. First, step one is still cache your GT results where it makes sense. Use that in-memory or browser storage for fast access to data that doesn't change much or gets read often.
Okay, handle the fast reads first.
Right. Then, for the requests you do actually send, whether they're gets you decided not to cache, or any post but delete operations, you need a way to manage them so you can cancel if needed.
Which means tracking them.
Exactly. Track your active requests. The sources suggest techniques like using a JavaScript set to hold on to all the active AbortController instances.
How does that work?
When you initiate a request, you create a new AbortController, add it to your global set, and pass its signal to fetch. Crucially, in a finally block for that fetch promise.
So whether it succeeds or fails.
Right. Whether it succeeds, fails normally, or gets aborted, the finally block runs, and you remove that specific controller from the set.
Okay, so the set always contains only the requests that are currently in flight. It's a live list.
Precisely. And now the critical connection. You set up listeners for those navigation or unload events we talked about, before unload, router changes, etc.
And those listeners?
Those listeners cancel on navigation or reload. When the event fires indicating the user is leaving, your listener just iterates through that set of active AbortController instances and calls abort on every single one.
Automatically cleaning up all pending work as the user navigates away. Nice and tidy.
Correct. And underpinning all of this, absolutely vital for writes, is that server-side consideration. The backend must handle idempotency, usually with those keys, and potentially have ways to clean up or roll back partial changes if things go wrong.
It really is a layered system then. Fast reads from cache, clean exits, and client cleanup via tracking and cancellation, and then robust, safe writes thanks to backend smarts like idempotency.
It is. It's about using the right strategy for the type of request and having those safety nets for the inherent unpredictability of networks and user actions.
So what does this all mean for you, listening? Based on these sources you shared, you can hopefully see how putting these strategies into practice directly affects how fast your application feels and how reliable it actually is, especially when users are moving quickly between pages or dealing with iffy connections.
We've looked at specific tools like the different caching options, the AbortController pattern, how to track active requests, and why backend idempotency is so non-negotiable for writes.
And the material also kind of hints, doesn't it, that while you can build all this plumbing yourself,
Oh, yeah. Many modern front-end frameworks, and especially data fetching libraries, things like React Query, SWR for React, or built-in capabilities in Angular or Vue services, they often provide abstractions that handle a lot of this caching and request tracking for you.
giving you some boilerplate.
Definitely. They can manage the cache, track freshness, handle background updates, sometimes even cancellation. But, understanding these underlying principles we've discussed makes you way more effective at actually using those libraries correctly, configuring them properly, and debugging when things inevitably go sideways.
Absolutely. Knowing what's happening under the hood is key, which I guess raises a final question for you to think about. Consider the applications you build. What kind of data do they primarily deal with? Is it mostly reading data, or are there lots of complex write operations?
Yeah.
Based on that, where do you think implementing better caching or more robust request cancellation would give you the biggest win right now? Or maybe where would it present the most interesting challenge to implement correctly?
Something to definitely ponder as you continue building.